For our next installment, we're going to take another look at Lenz's law. You saw a Word document about that a few days ago, and you'll recall that Lenz's law, as we've discussed it so far, tells us the direction of the current, and therefore the direction of the EMF, that results from the change in flux inside, for instance, this loop here. We see that we've got the copper bar moving right to left in our picture. It is the leftmost side of a loop that includes the black wires and the resistor all the way on the right. And it is this whole configuration is bathed in a magnetic field that is coming out of the board as indicated by the green dots. So that bar, as it moves right to left, results in an increasing flux inside our loop, and Lenz's law allows us to understand the direction of the current that results from the EMF that results from that increasing flux. Take a moment and think about what direction that ought to be. Hope you hit your pause button and thought about that for a moment. If we use our motional EMF model, we realize that looking at the right-hand rule, the charged particles that are part of the copper bar are moving right to left. They're in a field that's coming up out of the board, and therefore we can see my palm is pushing that way, making a current that flows up the copper bar. And just like magic, we see the current has been added to our diagram. It is flowing then in a direction that we would call counterclockwise. Motional EMF gives us that result. Thinking about Lenz's law and how the current tries to combat the change in flux gives us the same result. Let's take a moment and think about how we could apply that notion of the change in flux and the direction that the current would have to be to oppose that change in flux. Think about that for a second. And we're back. So inside this loop, the flux is getting greater. And the flux is due to a field that's coming out of the board. So any current that's induced must, in order to obey Lenz's law, must create a field that's going into the board. With this black marker, I'm going to draw the field created by the current that is induced by the increasing flux. Inside the loop, that field is into the board. All right, that's not the field that existed in the first place. That's drawn in green. Instead, what I have in black is the field that is created through the induced current, as any current would create a field, and inside that loop, that field must be into the board to oppose the increasing flux, where the flux is due to a field that is out of the board. Now we can just imagine grabbing the loop with our hand, with our fingers going into the board, and everywhere we grab it, try this, and I'm going to zoom out a little bit for you. Everywhere we grab it, we see my thumb is pointed clockwise, just like the result we got when we thought about the EMF. Okay, what just happened? Now we're looking at a much simpler situation. I've got just a plain old rectangle of copper wire for us in our imagination. And so that we're all thinking about the same thing at the same time, I marked one edge of the copper wire with some little black slashes, just so we can all talk about the left edge of the copper wire together. Think about that copper wire. Right now it's just minding its own business, but in a moment I will immerse that copper wire in a magnetic field. So hang on just a second and you'll see that. Okay, I hope we can see a lot of green dots on the board right now, and those green dots represent magnetic field lines coming from a magnet. Now that magnet would of course be right above the wire, and which side of the magnet do you suppose would be closest to the board if this were a bar magnet.